Okay, today we are going to discuss about a standard IEEE 1451. These standards cover the smart transducer interface standards. Okay, so it's a family of standards. It's not just one standard. And basically by this standard, we are able to have like a interoperability and plug and play functionality that makes the transducer connect into the network, to the smart network with a self description and self validation. And it's basically provide us with a requirement that allows different vendors or different network connect to each other. The transducer also connect to them, regardless of the design of the transducer and the design of network. Now, let's begin by defining what IEEE 1451 actually is. The IEEE 1451, as we said, is a family of standards. So it's not just one standard, it's a family of standards that were developed by the IEEE Instrumentation and Measurement Society. And the goal was to address the important and significant problem of the transducer interoperability. Now, these standards defines both hardware and software interfaces. So it includes the physical connection, the command structure, the transducer electronic data sheets, which we call it TEDs. And basically it made them work over wired or wireless or point-to-point system. So it provide basically a plug and play capability using a machine readable kind of like metadata. Now, there is some concept that we have to like talk about before we going through the details of this standard. One is that what is a smart transducer? What we mean by a smart transducer? Now, a smart transducer is not just a sensor or actuator. When we talk about them, it also includes onboard processing, self-identification, and self-description features that basically enables automation and integration. Now, these standards basically, as we said, covers both hardware and software interfaces. So it defines how devices are physically connected and how they exchange data and metadata with each other. This standard is network neutral. What that means? That means that no matter what type of network or connection you're using between the component of your system, it could be wired, it could be wireless, it could be point-to-point or multi-drop system. These standards define the family of the standards define all the requirements for regardless of the connection. We are going to talk about them in upcoming slides. So it's give us a universal kind of like situation. Now, there is an, as we said, plug and play capability. What we mean by that? So when we define the tests, true machine readable description that we have, which is short for transducer electronic data sheets. Okay, basically any sensor or actuator that comply with this standard can be automatically identified, configured, and validated by the host system. Okay, so The main goal in this standard is to provide an open and vendor neutral and network neutral framework for basically integrating the sensors and actuators into a digital system. Now, without these standards, basically the integration of these transducer is going to be a manual uh, with vulnerability to the error during the process. It will depends, those integration will depends on a custom mode. So there is some vendor specific drivers for each sensor and actuators, and it should be hardwired configurations because they cannot identify each other, the part of the system. So this is important. IEEE 1451 actually help us significantly to have the easier integration of that transducer. Now, the IEEE 1451 was basically developed in mid-90s. So the goal was to address basically the chaos that was actually growing because of the incompatible sensor interfaces in our system. So before this standard, industrial system basically have a very high cost and system failure because the non-standard sensor wiring and the inconsistent kind of like metadata and data within the system between the component create an integration issues. Okay, so this standard basically create a foundation for a modular sensor networks by formalizing a framework that transducer can communicate through a common protocol, basically. Now, over time, these standard family transform the regular sensors into intelligent, basically, nodes that can report their identity, calibration, and the status. So it basically create the foundation for having a modern smart sensing kind of like ecosystem and advanced technology of sensors, the instrumentation, the measurement, and actuators quite significantly. Now, when we talk about today's system, this IEEE 1451 actually is very important and plays a significant role when we talk about the IoT, the Internet of Things, or cyber physical system, which basically every system that we have is going toward to being a cyber physical system. And also it kind of like plays a significant role in Industry 4.0. We are going to talk about the definition of the 4.0 in this slide. So if you don't hear that heard that before, you know what we mean by Industry 4.0. Now, when we talk about the plug and play interoperability, this is a sensor level for IoT system, which use that TEDs that we talk about to basically provide a machine readable and a structured data. So it could be easily interpreted and by the middleware and cloud platform. Okay, so one of the important aspects of this standard is that it supports the legacy and a smart device. So when we talk about that, it means that all the old generation transducer also could integrate to the system. So it basically creates an ideal configuration for a scalable and hybrid kind of IoT deployment. Now, when we talk about a cyber physical system, those systems basically require a real-time response. Okay, so this standard IEEE 1451 makes sure that we have a precise synchronization. We have a traceability over the calibration in our system, and we have a robust feedback loops between the sensors and actuators. So these standards basically give us a deterministic timing and error isolation, which is very important when we talk about the closed loop control. Uh, and it have like example of the autonomous systems, or it is very important when we talk about the critical infrastructure. Now, we mentioned that this standard also plays a significant role in Industry 4.0. Let's first see what we mean by Industry 4.0. When we say that phrase, we mean the fourth revolution in industry, which is the current movement, the current advancement in industry that basically create a system-wide, automated, AI-based manufacturing system. So when you talk about the manufacturing line, all the components, all the parts of that manufacturing line and that factory basically become digitalized and connected to each other. It includes the processing time. So they collect the data. This is the Industry 4.0 in the manufacturing line. All the components collect the data. It clusters the data, processes the data, make decision based on real-time decision, actually based on the machine learning algorithm and a pattern recognition, and create an online control and automation through the system. Plus, it gives a human interface that kind of like the client that uses this system or manages the system also can have access to all the data, and it could respond to each kind of like failure or event that happening through the system. So it makes basically it's IoT for industrial line and industrial processes. Now, this when we talk about the smart manufacturing, basically IEEE 1451 make that system a self-describing hot swappable sensors, which allow the production line to reconfigure themselves dynamically and without any manual recalibration or rewiring. Okay. Now, as we said, this standard is vendor neutral, meaning when we talk about the transducer that are following these standards, is basically because of the general and base foundation of the protocols and requirement, it makes the a vendor-specific configuration to be not a factor in our system design. So it supports cross-vendor device deployment. Now, that TIT that we talk about and mention about is basically enable the sensors that report the degradation, or if they need a recalibration, or if they have operational drift, which basically give us the ability to have a predictive kind of like maintenance strategy when we also talk about the Industry 4.0. This is a very important kind of like aspect of that. Now, this standard is not just a communication protocol. Okay, so it's a foundation that give us the ability of having a scalable, interoperable, and self-managing sensor network. Okay, so it's basically is the foundation of the modern intelligence system. Now, today we are gonna explain the purpose and structure of the IEEE 1451. We are gonna identify and describe the main components. We are gonna talk about the teams. We are gonna introduce them: teams, end caps, and TEDs. And we are gonna talk about the system level models and data flow that are basically defined in IEEE 1451, and the design basic of the smart transducer network using these principles. Now, when we talk about the 1451 standard, the IEEE 1451, basically the vision is to have to have the sensors that could auto discover themselves. So it means that they could identify there is identify transducer capabilities. Okay, they could auto configure to the system, so it basically match acquisition engines to the transducer. They could auto validate their compatibility. Okay, and basically make sure that they are working in a healthy operational situation, and they could auto document, so they could log and record every data and measurement chain for kind of like the possible future auditing. Now, when we talk about the auto discover, basically the IEEE 1451 allows the system to automatically detect any connected transducer. Okay, so it basically can identify that transducer, can basically identify the capabilities of that transducer. It could basically identify the calibration status, okay, without any manual input. So it's all automated. Now, after the sensor is identified by the system, now system also can automatically configure the data acquisition settings. So it could all kind of like set the sampling rate or measurement range or filtering if they need it. So, and all of these happening because of the TED's metadata, through the TED's metadata. Now, beside those, when we talk about the auto-validate, basically these standards make the transducer able to have a real-time compatibility check. And they could assess the operational health constantly. So we could make sure that the sensor is suitable for the task or function that we have through the expected parameters that we want to like sense or give a command to the actuators. Now, every time there is a measurement happening, okay, there are such a metadata like sensor ID, calibration details, and like a timestamp of the log data, which basically automatically recorded through the auto documentation capability of the systems consistent with this standard, which give us a complete and auditable record of all the measurement check. Now, as we said, the vision of this standard is that any standard compliant transducer can be plugged into any compliant system operate instantly without rewriting code or adjusting a setting or modifying the drivers. Now, when we eliminate this manual configuration, we basically eliminate the human errors, and basically this standards reduces the integration time, make sure that there is no mismatches, or the make sure that the measurement accuracy across the system is properly happening, and we have that accuracy that we need. Now, there are several major domains of the application for this standard. Excuse me. One is the industrial automation when we talk about the Industry 4.0. So in that part, basically this IEEE 1451 give us a quick and error-free basically replacement of the sensors like load cells, temperature probes, or accelerometers, by basically allowing the machines and transducer to instantly read sensor parameters through the tests. Now, in a smart grid, this standards basically supports an accurate and time synchronized monitoring of the voltage, current, frequency, the power factors, and it's happening across our system, across our grid. Okay, and it use a built-in calibration and the temporal kind of like metadata that we get from the TEDs in our system. There is a application in aerospace system when we need a control through a distance, when we have like a virtual TEDs and remote calibration capability, which basically allow a multi-channel telemetry system. So we could reconfigure the system in aircraft or planes without physical access. You could imagine how important this is. We have a biomedical devices that use these standards to make sure that the sensors like ECG, EEG, or blood pressure basically annotated with the patient-specific metadata. It would have a precise calibration and basically enhances the both safety and the traceability within the system. Now, one of the strengths of IEEE 1451 is that it's a cross-domain adaptability. Basically, these standards offer a solution for smart sensing in any application when we have a sensor integrated or automated integration is very essential to our application. Now that we talked about why this standard exists and what is the importance of these standards, let's talk about the core architecture that exists within this standard. Now, the architecture of these standards includes several fundamental aspects. The first one is transducer interface module. We call it TIM, which is the interface of the smart sensor or actuator that we have in our system. We have TEDs, which we said is transducer electronic data sheets, which is some digital metadata that describes the transducer that we have. We have NCAP, which is short for Network Capable Application Processor, which basically bridges the system to the network and control systems. So we have a clean separation that allows scalability, and having a layered system design. And basically, NCAP is the connection between the team and the human interface. Now, that team transducer interface module that we talked about, introduced, is basically a local hardware. It could include one or more sensors or actuators with a signal conditioning circuit, some converters, analog to digital or digital to analog converters. It could include a microcontroller to manage the low-level operations and basically receive the raw data, have a pre-processing, and make it suitable for the next level, which is the NCAP, which is basically processes fully the data and give us the result. Now, the tests that we introduce is, as we said, is a digital metadata structure, okay, which is either stored to the team or linked to the team, okay? And what is in the text is like an essential self-identifying information, like sensor type or measurement range or resolution or calibration data that basically defines what is the characteristics of that transducer so the system could know what kind of component it deals with and what is the characteristics of that component. Now, we have a digital interface which basically defines a standard communication protocol between the team and the NCAP. Okay, so it's the structured data exchange and command execution, regardless of the physical medium that we use for the connection between the team and NCAP. It could be wireless, it could be several type of wire. The configuration is different. Regardless of those, it creates the protocol, a standard protocol for data exchange between the team and NCAP. Now, the NCAP basically acts as the system's network bridge, which collects the data from one or more teams, process it, add a timestamp, and basically forward it to higher level application. So this architecture gives us a modular and decoupling hardware, which is a team, and it's distinct from the application software, which is the NCAP. So we have a flexible deployment, we have a distributed control, and basically it's a scalable integration of the transducers. Now, because of this standard digital interface and the TEDs that we talked about, basically any team, any transducer interface module can be integrated into any compliant NCAP. So we don't have to reprogram or manually set up those. So that's why we say that it provides us a plug and play integration when we wanted to like use the transducer in our system. Now, each transducer becomes, as we said, a self-describing tool because it has the TEDS information, meaning that basically system automatically knows what the sensor is or how it behaves or how to communicate with this sensor without any human interaction or human input. Now, we talked about some of the most important. Let's go a little more into the details. Let's talk about the team, the transducer interface modules. Uh, as we said, the team normally includes an actual sensors or sensor, one or more, okay, or actuator or actuators. So it could be one sensor or actuators or multiple sensors or multiple actuators. And it normally have the local electronics circuits that, for example, is maybe a signal conditioning circuit or analog to digital or digital to analog converters. It could include a timing source or a microcontroller for the internal management in the team. Now, before we convert the data to the digital, basically a raw data, which is an analog signal from the transducer, is basically processed using some amplifier or filtering, or if we need a linearization circuit, we could do that. Basically, all this happens so we could make sure that we have an accurate and noise-free measurement. So it's a pre-processing to enhance our measurement regarding the accuracy and noise. Now, after we have that, then the analog to digital converters kicks in. Now, why we need to change the analog signal to the digital signal? Because we know that analog signal uh, is very kind of like vulnerable to the noise and interference, the EMI interference. Now, if we change that to a digital data, we have a better kind of like and more trustable information, and it's more suitable for current technology in processors and signal basically control. Now, these converters basically are used for the sensors, okay? The analog digital converters are used for the sensor, so it gets the analog input data from the sensors after that pre-processing, and you turn it to the digital signal. So for the main kind of like processing to send to the end cap. But when we talk about the actuators, basically we wanted to like command the actuators. So we have output of the end cap processor or digital processors, and we wanted to like use a digital to analog converter, so we could have analog system signals for commanding the actuators. Now, each of the team could include also its own clock source. So we have a precision timing and we have a synchronization when we talk about the data sampling and communication, especially when a real-time or time-sensitive application, we need those synchronization in those applications. Now, the microcontroller that we talked about that could be included in the hardware modules of the team is basically a built-in microcontroller that handles all the data acquisition, the timing coordination, and TED's management within each team. So it's internal in each team. Now, as we said, a single team can have multiple transducer channel, like pressure or temperature or humidity, and share a digital bus internally and basically present a unified interface for the end cap. Now, each team basically uses a standard digital interface. It could be SPI, I2C, or BLE. We are going to talk about it a little bit. So it could send the data and the metadata to NCAP and make sure that we are consistent with the IEEE 14 1451 to make sure that we have a relevant standard data for the interface type. Now, wireless team, there is a wireless team that extend that architecture, okay, by having an RF communication module, okay? So we would have a remote, basically, deployment without the physical cabling and physical access, and make sure that we are still fully compatible with the IEEE 1451. Now, the TEDs that we talked, okay, is locally stored in each team. So it's basically the tool that enables that system to automatically identify each component and initializing the process in the system. So the team basically acts as a embedded intelligence in the physical layer. Okay, so it interacts with the environment, it processes raw signals, and encapsulate the result in a standard self-describing format uh, in uh, in a digital data. Now, we talked about and introduced the NCAP, which is a network capable application processor, which is basically an intelligent gateway, basically. So NCAP communicates with one or several multiple teams. The communication could be wired or wireless, so it doesn't matter what type of communication we have between the NCAP and teams. And it handles the command transmission or data acquisition and like metadata retrieval based on the protocols that are defined in IEEE 1451. Now, as we said, one NCAP can manage multiple teams at the same time. So it basically gives us the ability to have a centralized control system and a centralized data aggregation when we have a distributed sensing system like smart building or industrial plants. And this NCAP basically reads and writes the text, so it allows the system to identify each sensor or configure the acquisition settings and maintaining and record each device's specification and the status. Now, when we have the raw sensor data from the teams that are formatted and time-stamped and maybe optionally buffered by NCAP before being transmitted to external system, we make sure that we have data integrity and we could trace the data in respect to time. So it's as a temporal traceability. Now, most of the NCAPs run an embedded control logic. So they could execute the task like local decision making or filtering or control loop processing before they send the data to a cloud or an enterprise system. Okay, so those are clients, the end receiver of the data. Now, That end cap is also responsible for basically associating a high resolution timestamp. And it happens for each data cell. It is very important for when we have the application that are time sensitive, like closed loop control or synchronized logging. And the NCAP serves basically as a gateway between the transducer networks, all those teams, and the outside world, which are the clients. Now, using that network bridge, basically NCAP integrate with a platform or like a SCADA system, which allows a remote access and monitoring and control capability to the users. Now, in practical system, an NCAP might be an industrial microcontroller or a smart factory controller or a wireless edge gateway, which basically they aggregate the data from the several teams and transmit that to the client or user. Now, we talked about the teams and NCAPs and how they exchange some data with each other. There are several common interfaces between the team and NCAP. So team are responsible for uh, getting the data from the sensors, okay? Pre-process it, make sure it's accurate and noise-free. Convert it from analog to digital, and then send it to the NCAP. And when we talk about the actuators, NCAP is going to send the commands to the team, which would convert the digital data to analog. If there is a filtering or resolution or accuracy processing needs, the team would do that, and then it would send that processed analog signal to the actuators. Now, when we talk about in both type, sensors and actuators talking to NCAP, there are several type of interface that we could use on that data transmission. Now, this standard family that we talk about, the 1451, provide a specific description and requirement for each type of interface that we can use for exchanging data between teams and NCAP. Now, we could use a synchronized or asynchronous connection, which is the SPI and UART. These are the examples. And IEEE 1451 Part 2 covers that. In that specific part, the team and NCAP basically communicate using a synchronous, like SPI, or asynchronous, like UART, serial lines. So it provides a low latency, a point-to-point connection, which is ideal for embedded or real-time system. Now, another type of interface is CAN, which the part 3 of this standard covers. And basically, it uses a CAN bus to support multiple teams sharing a common communication channel. So it's very suitable when we talk about a distributed system, okay, like automotive or like robotics or industrial automation networks. But that's not the limit. We have another type of interface, which is I2C, multi-drop friendly serial interface. The part 4 of IEEE 1451 covers that part of that type of connection, which that I2C is a simple, cost-effective bus for mixed signal application, support analog signal transmission, and digital TEDS overlay. So it's basically what we use when we want to use a legacy sensors, the old version that are not compatible with the IEEE 41 or like they are not smart. When we want to connect those into the system, we use I2C. Okay, so we make sure that everything is still in the system consistent with the standard. Now, we have BLE or Zigbee, which is the wireless mesh or point-to-point connection between team and NCAP. The part 5 of IEEE 1451 uh, covers that and defines basically the wireless interfaces that enables a remote, basically teams to NCAP interact, which application of this kind of interface is in mobile or wearable or a smart infrastructure system. Okay, we have a low power tag communication, which we know it as RFID, which is one of the examples. Part 7 of the 1451 covers that type of interface. And basically it leverages the RFID for like low power or ultra low power communication with the transducers. So it basically allows a passive or battery kind of like assisted sensors to transmit the identification and the measurement data inside the system. Now, regardless of the interface type, all the protocols should support the IEEE 1451 commands like reading and writing data or accessing TEDs. So we make sure a consistency across the communications. Okay, so each interface required to include a robust error checking mechanism. Okay, so we could maintain the data integrity between the team and NCAP. It also, when we talk about the time critical application, okay, so there's time sensitive application, that interface should support clock synchronization between the team and NCAP. So we make sure that the time stamped measurements are accurate and consistent through our network. Now, this architecture, because it defines different type of interface, basically is give us a flexible architecture that allows the designer to select the type of interface that is most suitable for the application that they want out of this network. So we could have a wired system for precision or wireless system interface for mobility and without losing the compliance with IEEE 1451. Now, this standards would provide us with a uniform digital protocol definition, which basically runs over the diverse physical layers. So we make sure that we have interoperability and scalability through different deployment scenario that we have. Now, we introduced the TEDs and we said, okay, the TEDs includes the identification data, characteristic of the the teams, the transducers, and basically all the information that system needs to identify and validate each team. But TEDs could include several type of data. Now we have meta TEDs, which is basically the global device info. We have channel tits, which is the range and unit and resolution for that team. We have the calibration type of tits, which is information like offset or slope or nonlinear mapping that the sensor or actuator would have. And we have a user tits, which is covering the like a human readable labels. So we could understand on a human level, on a user level, what's happening inside our system. Now, the TETs, as we said, are digital metadata structure for each transducer, okay, which basically make them able for each sensor and actuator to describe itself automatically to the system. So we have self-identification capability, we have a plug and play capability. We can store the information locally within a team, and which basically allows a flexibility in cost and memory constraints. Now, that metadata that we talked, as we said, it includes global information. Okay, so and it's normally used for system-wide integration. The transducer channel give us channel-specific details like physical quantity. It could be like a temperature, the range, the resolution, the engineering unit, which basically allows a precise integration of each signal in the team, in each team. Now, as we said, calibration test stores sensors data like gain, offset, polynomial coefficients, or other transfer functions that make sure that the measurement data is both accurate and traceable. Now, the user transducer name is an optional section which basically allows users to assign human readable name or comments or asset tags to the sensors. So it would help us in the maintenance or auditing or multi-sensor management. Now, we talked about the architecture of the system. Now let's see what actually happened to the data within that architecture. Now, the process starts and begins with physical parameters. It could be temperature or pressure or humidity, which is basically detected by the transducer as a sensor, and it's an analog signal. Now, when we get that analog signal, that raw analog signal, then we run some pre-processing, which is it could be we need to like amplify it or filter it, or possibly we need to linearize it, which we use some signal conditioning circuit inside the team so we could improve the measurement fidelity. Now that we conditioned that analog signal, that condition would be digitalized by an analog to digital converter. Okay, so we make sure it's ready for digital processing. After that, there is an embedded processor, okay, inside the teams, which basically combines that digital signal with some relevant metadata, which comes from the tests, like calibration parameters, units, resolutions, okay? And when we add those metadata into that digital information, now the data is basically transmitted over that interfaces, one of the interfaces that we talked about, from the team to the end cap. Now, end cap receives that data. It added a timestamp on it for the logs and records that we need, and basically perform some required processing or diagnostic over that data, and format the data according to the application and network protocols. At the final step, that processed and timestamp data will be forwarded to the client. It could be an analytic engines or cloud platform or a visualization or a long-term storage or even a decision-making system. So each step in that chain from the physical signal to the client, to that endpoint, that end-cap would send out the information. As you see, all of them are modular and all of them are observable. So system errors can be isolated and traced through all the metadata tagging that we have in this data form. Now, the metadata that we have from the threads basically follows the signal at each step. So give us a full traceability for auditing or quality control, or if we need a fault diagnosis or a compliance analysis. So we make sure that we can trust the data that is transmitted to the user or the client. Now, teams basically operate based on the defined states, like initializing or active accusation. But NCAPS works on scheduling or configuration or multi-device coordination. This is the difference between the process within the teams and the general gist of the process within the teams and the NCAPS. Now, as we said, IEEE is a family of standards. No, it's not just a single standard, okay? And each part is designed to handle different physical interfaces or communication topology or a transducer configuration. Now, part 0 is the foundation layer. That part defines the common command set or data structures and text format, which makes all the standard family to have a unified definitions, okay? And it's consistent through all the other parts. Part 2, which we mentioned in the interface, covers the point-to-point digital interface, which specifies a direct digital interface between the team and NCAP using a serial protocol, which is ideal for embedded or low latency application. Part 3 covers the multi-drop network interface, which supports bus-oriented communication when we have multiple teams that share a single channel with the NCAP. Part 4 is mixed mode interface, which combines the traditional analog measurement lines with the digital TEDS metadata. So we could have the ability to basically have the legacy transducer, legacy analog transducer, so make them able to participate in smart sensor networks. Part 5 covers the wireless communication protocols, which defines how teams can communicate wirelessly with the NCAP. Okay. Very suitable for mobile or remote sensing system. And all the substandards that we talked are unified to a consistent metadata model which basically makes sure, regardless of the communication method, sensor data can be uh, interpreted the same way into the system. Now, let's go deeper into some of the most important parts. One is part two, which is a point-to-point digital interface. As we said, this is defined a point-to-point digital interface that connects one transducer interface module, one team, directly to one NCAP. Now, this type of interface uses a fast and simple serial protocols. Okay, so it makes sure the reliable, low latency data transfer between a team and NCAP. It's especially suitable when we talk about the embedded system and when we need like a deterministic performance or fast response time. Okay, so we have a dedicated communication channels, uh, which is very important for those applications. And because it uses a direct link without any shared bandwidth, okay, it gives us a high speed data acquisition. So it's very good for time sensitive application like motor control or real-time monitoring. Now, this standard includes commands for discovering and reading the text from the team, which allows the NCAP to automatically identify and configure the connected transducer. It also provides an optional support when we talk about the synchronization between the team and NCAP. So we are able to have a consistent sampling intervals, okay, and like an accurate time stamping. This interface also supports basic self-test features, uh, which helps detect the faults or calibration drifts at the point of measurement. Uh, Common application for this type of point is like engine sensor modules in automotive systems, embedded medical devices, robotic actuators, when we have a local microcontroller to sensor links, and we need those type of direct links. So the primary advantage of this part basically is the electrical simplicity and deterministic communication, which basically makes that very ideal for tightly coupled and high reliability applications. Now, we have two other common standards, very popular standards. One is the part three, and another one is part four. Part three covers the distributed multi-drop interface, which basically defines a multi-drop communication interface when we have multiple teams and they are connected to a single NCAP and they use a shared bus. So that is very good for distributed transducer network. This part is designed for a bus-based topology. Okay, when wiring is minimized and the device share the same basically communication medium. So each team on the bus is assigned a unique address. So it allows the NCAP to pull and communicate with each of the transducer individually. So there is no collision and arbitration. Now, because all the teams share the same physical bus, so it significantly reduces the wiring complexity and cost, which is very beneficial when we talk about a larger scale installation like factories or buildings. Now, that standard supports automatic discovery of all the teams on the bus, so it's also a plug and play functionality. Okay, when we have a dense and shared network environment. And it's commonly used in a factory automation or remote I/O panels when we have multiple sensors or actuators and they must be monitored and controlled from a central processor. Now, part 4 of these standards covers mixed mode interface, which is a hybrid approach that combines an analog signal line for sensors data with a digital interface for TEDS metadata. So we can have the legacy analog transducer to be introduced into a smart networks. Now, this part basically give us a backward compatibility. Okay, so we can use the existing analog instrumentation while we could enhance them with a self-identification and plug-and-play feature. Okay, so the digital TED is transmitted through a separate pin or modulated over the analog line using techniques like digital superposition, and it makes uh, possible to add metadata without disturbing the original signal. Now, this mixed mode interface basically allows the system to gradually transition from the traditional analog system to fully digital smart sensor without replacing the entire sensor infrastructure at once. Okay, so we could gradually enhance our system. Now, it's ideal for upgrading the system, legacy system, and basically is like the aerospace instrumentation or thermocouple networks. So we could embed a small chip that contains TEDs directly into the connector or sensor housing. Now, this is our discussion about the smart transducer and the IEEE 1451. If you have any question, please let me know. Otherwise, thank you for your attention to this